I think would not be counted because his proper name is not displayed.
Okay, we can start. Another thing for taking attendance will be devising one policy that okay during the lecture at any point of time 5 students or 6 students or 10 students will be called at random. Maybe say I can call during after giving 2 minutes pause. I can call say 110 to 120. Okay, and during that time, if you are present, then it is possible to give your attendance. So this is we are devising because we want that everybody should listen this lecture. It is not the case that you will not be listening the lecture. Okay, you will be muting yourself and you will be sleeping. So any point of time, your attendance might be taken uh, in pen and paper. Okay, so be ready for that, right? Okay, so we can start our today's lecture, and আচ্ছা, এটা ইউজ করবো নাকি এটা এটা ইউজ করি নাকি দরকার okay. Okay, so we were dealing with graph theory, and uh, in that graph theory you have motivated that okay we are having several different applications. Oh, okay, I haven't shared the screen. Is it visible? Is it visible?
Yes, sir.
Okay. So in this, we are discussing that graph algorithms, and we have seen several different applications of that graph algorithm. Now, what we are trying to do is we are asking that what kind of questions. So, say this protein-protein interaction graph or this Facebook graph is like this, then we are no longer will be telling that this is a Facebook graph or this is a protein-protein interaction graph and so on. What we'll be now looking for is the abstractness of the graph. That means we are having nodes and we are having say connections between the nodes. Okay, so that it might be fitting in several different applications. Okay, so that's why the graph is the one of the most highly rated abstraction of computer science. Okay, abstraction means it is fitting in several different applications. Okay, and in the last class we have seen okay we can ask if this is there are graphs like this, then we can ask these are the questions we can ask. So these questions we can also ask that Euler cycle. Okay, so is there a cycle that uses each edge exactly once? Okay, is there a cycle? Say whenever say we are having this type of say graph, Okay, say this is a graph. Okay, and whether this Euler cycle is or Euler tour is existing or not, right? And from there, the graph theory took off. Okay, so graph discovery was actually done with that bridge problem by Euler. Okay, uh, Königsberg bridge problem by Euler, and there he was asking these questions. Okay, say we are starting with this source vertex, and then is there a path existing? Is there a cycle existing that will be covering each edge exactly once? Each edge exactly once. Okay, and then it will be coming back to its source node. Okay, so we are seeing that in this case we are having. Okay, so if you look at this case, then he pointed out that okay, the degree of this vertex, the degree, that means the edges which are incident on this vertex, the degree. Okay, so the degree of each vertex is even. So this, the degree of each vertex is even. This is having degree 2. Two edges incident on this, and this this vertex having how many? What is the degree of this vertex? Can anybody tell? What is the degree of this vertex?
Sir, 2.
Huh? 2.
Sir, 4.
Who is telling 4?
Sir, me.
What is your name?
Sir, Amit.
Amit, roll number
102.
102. It is 4 because this vertex having incident edges, this one, this one, this one, this one. Okay. And the degree of this vertex is again 2. So we are seeing that whenever we are having the degree of each node is even, then we are having the Euler's proof that okay, we are having some kind of Eulerian cycle or tour existing in the graph, right? And this will be coming in one of the approximation algorithm whenever we'll be discussing. Okay, this Euler cycle will be coming, and but you see here whenever I'm going for these stages, okay. So now you see whenever I'm coming back here, whenever I'm coming back, okay, whenever I'm coming back here, so but at that time we are visiting nodes 2 times. It may be the case in Euler cycle, we can visit the node many times, but the edge is to be explored only once. Okay, and the exactly opposite kind of idea is put forward in Hamiltonian cycle, and this Euler tour calculation is polynomially solvable. Okay, so far there is polynomial time algorithm for this, but this Hamiltonian cycle. Okay, so if they say this is a graph, say this is a graph, this is a graph. Okay, and this is a source vertex. This is the source vertex. Then we are asking that is there a cycle that uses each vertex exactly once? So we are seeing that okay, whenever I am taking this path to reach there, then this path to reach there, then this path, then this path, then this sorry, then this edge, this edge is I am taking, and I am coming back to its original vertex. Okay, where from we start. Now you see on the way we are visiting nodes exactly once. So this is the Hamiltonian cycle problem. But we very often call this is the Ham cycle. and this is, but whether in a graph, okay, so the graph might be like this, right? It might be even complicated one, and in those graphs, okay, in those graphs, whether we are having this hand cycle existing or not, that is yet to be solvable, or we do not know yet any kind of polytime algorithm for this. So this is, you see, whenever we are talking in terms of edges, it is becoming simple. But whenever we are talking in terms of nodes, it might be difficult to have the polynomial time algorithm. Okay. So this is the beauty of computer science, and this is the beauty of algorithm. Actually, computer science mean we are finding the algorithm. That is everything. Every time we are asking whether it is computable or not. Okay. Okay. Yeah. We are taking attendance. We are taking attendance. So roll
Okay.
number one.
One present, sir.
Roll number one.
Sir, two
Present, sir.
present.
Present.
Roll number two.
Present, sir.
Roll number three. Four.
Present, sir.
Five.
Present, sir.
Roll number six. Seven. Eight. Nine.
No.
10. 11.
Present, sir. Sir, 11.
Okay. 12.
Present, sir.
13.
Present, sir.
14.
Present, sir.
15. 16.
Present, sir.
Okay. And listen carefully that this attendance we have taken, we can come back to this attendance again. Okay. So it is not the case that your attendance is taken, then you will be muting and you will be sleeping. Okay. So be aware about that. You must have to attend this class. Otherwise, attendance you might not be getting. Okay. So we can come back what we were discussing, and this is again one connectivity problem. Okay, is there a way to connect all the vertices? Okay, so if this is our graph, okay, if this is our graph, say, right, so now we can think of, say, okay, this connectivity problem could be, we will be discussing in terms of, say, MST, minimum spanning tree. So this there could be a minimal connection which can connect all the nodes of this graph. Okay, so this could be a minimal connection from this graph, right? So this is called the minimum spanning tree problem, or this is spanning tree problem. And minimum spanning tree, whenever we'll be adding some kind of edge weights to it, and then we'll be defining what is this minimum terms we'll be defining whenever we'll be discussing this. This is the spanning tree of this graph. Okay. In some minimalistic way, we are connecting nodes of this graph. Okay, right. So this connectivity problem we can again ask. And what is the implication of this connectivity problem? because if we want that these are the some localities where we have to lay some kind of wires from this electricity department. So then how much minimum wire to be deployed? So that one can be tackled through this spanning tree problem, okay, or rather this minimum spanning tree problem. This is again another kind of connectivity problem. Okay. So this biconnectivity, this biconnectivity problem is there a vertex whose removal disconnects the graph? Okay. So maybe if I'm having say this graph, okay, this graph, right? Then if I'm removing if I'm removing this guy, then whatever graph we are having still remaining, are they connected? That means we can reach from here to here. We can reach from here to here. Okay. So you're seeing that okay, even if I'm removing this guy, we are having the remaining graph still connected. Okay. So it is a biconnected graph. Okay. But think of this kind of this graph. You think, right? And this is our node X. If I am removing this guy from this graph, then we are having uh, this type of subgraphs. Okay, this node is there. So now you see this the graph, the remaining graph which we are having. So this is the remaining graph, and you see we cannot reach from here to here. Okay, right. So this graph is not biconnected. Right. So this kind of question we can ask. Okay, I give you one exercise that can you think of one application of this? Okay. Now this planarity is hugely studied in graph theory. Okay. So can the graph be drawn in the plane with no crossing edges? That means say this is the graph. Okay. Right. So this is the graph. And you see the edges are crossing. So these two edges are crossing. But we can draw this graph separately as well. We can have this and then, sorry, we can have this and then you see this edge. This edge can be drawn like this. Okay. So this graph, even if it seems that it is not planar graph crossing edges, but it is actually planar, right? And there are graphs, okay, which will not be planar graph, okay. So you cannot draw that graph without crossing the edges. The crossing the edges must be there. Okay. And another interesting case we ask that graph isomorphism, okay. So that means say this is the graph connection, okay. And maybe we can have a graph structure like this. So you see this graph is reoriented and is drawn like this way. So we can ask that whether these two graphs are same. Maybe at that time we can ask a similar question, that is, do two adjacency lists represent the same graph? Okay. So this the representation of the graphs we can do with two ways: adjacency list and adjacency matrix. Okay. So so this representation we are coming next, but these two adjacency lists representing the same graph. That means these two graphs these two graphs are isomorphic, but there are examples that the graphs are not isomorphic. And this is an uh, interesting field of study. Still lots of work going on in this graph isomorphism. Okay. Okay, so this graph and its related ideas we have got. Okay. Okay. So as I was telling that, okay, we can represent the graphs with two ways. One is this adjacency matrix, and another is adjacency list. Okay. So now you see this adjacency matrix of a graph G equal to V comma E. These are number of vertices in the graph, and this is number of edges. Okay. Say if I am having this graph, okay, this graph. So how many vertices in this graph we are having? Can you tell me? V. How many vertices?
7. Sorry, four. This one, 4.
So this is four vertices. Who is telling?
Sir, Sagnik.
Huh?
Sagnik, sir.
What is your roll number?
16.
16. Roll number 16.
Yes, sir.
Huh.
116.
16. Roll number 16. So this is we are having A, B, C, and D, right? So these are the number of vertices, and the edges we are having. How many? How many edges we are having?
4.
4.
Four edges. Roll number 16 is telling. Who is telling
Yes, sir.
four?
Sir, 142.
Huh?
142, sir.
142. Okay, so this is AC one edge, then CD another edge, then say AB another edge, and then BD is another edge. Okay, so these are edge set, right? And as I told you that we'll be forgetting everything, applications and all these things. Now we know what the graphs are. We'll be representing graph with this abstraction. How many vertices we are having? How many edges we are having? Okay. Now this vertices are numbered 1 to cardinality of this V. Okay. So cardinality of this V is 4. Okay. 4 number of vertices are there. So vertex might be represented like this way also: V1, V2, V3, V4, like this. So it will be numbered 1 to cardinality of V in some arbitrary manner. Okay. I can represent this as V1, this as V2 as well. This is V3, this is V4. Okay, like that way also. Then the adjacency matrix representation of a graph G consists of adjacency matrix. So these many entries, V cross V. Okay, and we are defining that matrix by A, and this is we are having this each of the entries is denoted by Aij, and such that if Ij belongs to this H set, we will be having 1, otherwise we will be having 0. Okay. So for this graph, what we are having, so this is 1, 2, 3, 4, and this is 1, 2, 3, 4. Okay. So this 1, 1, here 1, 1, whether it is having an edge, we are seeing that no. So it will be 0. And this 1, 2, 1, 2, we are having one edge. So this will be 1. 1, 3, if V1, V2, V3, V4 is like this, can you tell me 1, 3 having an edge or not?
No, sir.
Who is telling?
Sir, roll number 172.
172. Okay. So 1, 3, as I am saying, this V1 to V3, there is no connection. So it will be 0. And 1, 4, we are having one connection. This is 1. Now we are taking 2, 1. Whether there is one connection. 2, 1 having a connection? Yes. 2, 1 having a connection. And then this 2, 2, not 2, 3. 2, 3, we are having a connection 1. And 2, 4, we are not having a connection. So this is the way we are having one matrix like this. And this matrix is called this A. Okay. And it is consisting of each element of this matrix. Each element, say this is, or say this is, each element is represented by Aij. Okay. Okay. So this is the adjacency matrix representation of this graph, right? And you see that whenever we are representing like this, many entries might be 0. So like this, many entries. Many entries might be 0. And generally it is observed that the real life graphs are sparse. That means many edge connections between nodes are not there. Okay. So as this V1 to V3, we are not having any connection, but still we have to represent that in the matrix because by 0, by putting a 0 to indicate that we are not having a connection. Okay. So if I am having a gigantic network 1000 by 1000, okay, and most of the entries are 0, then we can say it is wastage of memory. Okay. Only one we can keep track, that means which are the edges having connections. Sorry, which are the nodes having connections, right? So if I am representing with this adjacency matrix, we might be in trouble whenever the graph might be sparse in nature. And many real life application which we are modeling with graph, it is observed that this is sparse in nature. Okay. So adjacency matrix might not be a good representation in many cases. Then what we got to do? We have to have another representation which we call this adjacency list representation. Right. So this is uh, for each. So whatever graphs we had earlier. So this is V1, V2, maybe this is V3, this is V4. Okay. Right. So we are taking attendance again. So
Roll number 117.
Present, sir.
18, 19, 20,
Present, sir.
21, 22, 23,
Present, sir.
24, 25,
Yes, sir.
26, 27, 28,
Sir, present. Sir, 20, sir.
26. Okay. 27, 28, 29,
Present, sir. 29.
30, 31,
Present, sir.
32,
Present, sir.
33,
Yes, Prof.
34,
Present, sir.
35.
Present, sir.
Present, sir. 35.
Roll number 1,
Present, sir.
roll number 2,
Present, sir.
Okay, so we are coming back again. This is this V1, this node number 1. Okay, so it is having connection to two nodes. It is having connection to two nodes like this. Okay, so we can have so this V1 having connection to these two nodes. So this is V2 and then this V4. So likewise this V2 whenever I am doing, so this V2 will be having connection to nodes V2, V1 and V3. So you see this if this is our graph, this graph we are talking about, then that's one representation. Okay, one, or this is the graph actually, the whole graph. So this is the whole graph, right? And its representation is adjacency list representation is shown here. That means for each vertex, how many nodes it is connected with, only those information we are keeping track. But in adjacency matrix, we are keeping track of the, say, whenever we are talking about this node, we are keeping track that with which nodes this node is connected with this node and which node it is not connected with also. So if I am keeping track, it is connected with this, implicitly I am taking care of with which nodes it is not connected. So it is a huge saving as far as memory is concerned, right? If you imagine that this is a 1000 by 1000 matrix, then it's a great improvement, right? As far as space is concerned. So you see this 0, the node 0 having connection to 6, 2, 1 and 5. So it is represented like this. So here we are representing, say, this node 0 is connected with 6, 2, 1 and 5. So like this 1 is connected to 0, 1 is connected to 0, right? And so on. Okay. So this is the way of representing adjacency list. And we have seen that what is the advantage of having this adjacency list and then this adjacency matrix. Now exercise I can give. Is there uh, any advantage advantage of adjacency matrix representation. Adjacency matrix. Should we consider adjacency matrix at some point of time also? So that is the exercise you think. But the thing is that whatever algorithm we'll be discussing here, until stated otherwise, every graph representation will be based on this adjacency list, AL, adjacency list, adjacency list. Okay. So in practice, we use adjacency list representation. Okay. Now we are going to this breadth first search. There are two searching techniques of the graphs. That means we can start from a source node and we can explore the graph. Okay, that is called the searching of the graph. So this we'll be discussing right now a little bit about this breadth first search. So let us find out the applications of this breadth first search. Okay. So there is the first application that we can have is this Facebook network. Okay. So if a graph like this, we are having, say, like this, if a graph we are having like this, then how Facebook is recommending, say, this guy is there. This guy I am targeting. I am the Facebook algorithm, and then I am targeting this guy, and I'll be trying to recommend this guy some friends. Okay, that okay, these are the guys which you might be knowing and you might be connected with. Okay, and we get this kind of recommendation. So under the hood, the Facebook might be running the BFS algorithm, breadth first search. So in the breadth first search, what happens is that we are starting with a vertex, and then we explore all its adjacent vertices, this one, and this one. So we explore this level 1 first, and then whenever I'm taking this level, all these nodes will be taken in this level, and then all the adjacent vertices of this level, that means these nodes, will be explored. Okay. So for this Facebook network, the thing is that this is the guy whose direct friend is this guy and this guy and this guy, the direct friends. And these are the friends which are friends of friends. Okay. So for whenever I am targeting one guy to be recommended with friends, then I am exploring the graphs with the best Facebook network. Breadth first search. Just a minute. Hello. Hello. Look at it. Ah. Okay. So this then the breadth first search, what it will be doing, it will be exploring this level, all the nodes, and then it will be going down one level, say, or maybe it might be going down some k levels. Okay. And then it will be recommending all these friends of friends, to this guy. Okay. And it will be telling, okay, you might be the friends of these guys. these guys, right? So this is the simplest application of the breadth first search. The Facebook network maybe as a first place, they can apply the breadth first search and they can extract some modified breadth first algorithm. Breadth first search, what it will be doing, it will be exploring all edges of the graph. But what we want for Facebook, it's a gigantic network. So we are having many levels down, and those many levels, if we are going, there is no point uh, exploring all those levels, because friends of friends of friends of friends, if I am having say 2 3 levels down, then there might not be having any connection. I might not be having any connection with all those levels, okay, down. So it's some kind of modification of breadth first search could be applied in this Facebook network, okay, to recommend friends. We are recommending friends. So this is a nice little application, recommendation of friends. Okay. That we can do with this breadth first search technique, right? Now, this routing network we have already discussed whenever in the first class, that okay, this is the routing network, this is the communication network. Whenever you are the NIT Durgapur is sending packets to say Amazon, it is visiting several nodes, and then it is going to this say Amazon server. So all these interconnections we can have, all these interconnections we are having, and the routing table of your NIT Durgapur will be having this map, okay, right? And then I can reach from this NIT Durgapur to this Amazon by this path, by this path, and also by this path, okay, or this path. So now this, if I compare this path to this path, then we will see that okay, whenever if I am taking this path, then I need to hop 3 edges. If I take this path, then I need to hop 2 edges. Okay. So these 2 edges might be profitable for me, and I'll always be sending say the packets to these 2 hops, okay, through this 2 hops path. So this is again a shortest path problem, or if the edge weights are not there, then we can think of it is a BFS problem, breadth first search problem. Why this is breadth first search problem, we will be seeing after, as we are discussing. Whenever the discussion of breadth first search will be over, then we will be appreciating that okay, the breadth first search can also be utilized for shortest path whenever edge weights are all one, or we are not having any kind of edge weights. Okay. So this is the one application, again another application of this breadth first search, right? Okay. Okay, so we'll see 2 more examples of breadth first search, and then we'll uh, we'll discuss the algorithm. And then tomorrow in the next class we'll be having this breadth first search and depth first search. I think that up till depth first search will be covering in the next class. Any question?